Today in Math for Life, we're going to be doing 4.5 exponential and logistic functions. You are going to want to make sure you have your calculator out to do this. If you do not have one, you can borrow one, but you do need to leave your cell phone with the teacher in order to borrow one. So we've already looked at linear functions. That's what these ones were. Now we're going to be looking at exponential. The difference with exponential is that the variable is in the exponent. They may look similar, but they are very, very different. So on the next slide here, what their graphs. The blue is linear, obviously that's a straight line. The green is exponential. We did these a little bit when we were doing banking back in the first quarter, but as you can see, the longer it stays, the quicker that it grows as it's going. So it starts off with kind of slow growth and then starts going really quickly. We'll talk about exponential growth and exponential decay. Growth is obviously where it's increasing, like the one on the left. Decay is where it is decreasing, like the one on the right. And the way that we tell if it's decay is the negative. Notice this one here, the value is a positive right here. So that one is growth. The one with the negative in front is decay. We also need to understand the E value. E is just a number, kind of like on our calculator. We have pi. There's a button for that. There is also a button for E on your calculator, and E represents approximately 2.71828. Like pi, it keeps going forever. On your calculator, the button that you'll use, there's a button that it's on the left-hand side towards the top, and it has an E with an X like that. That's the button that we're going to be using as we do these. This page in your notes is going to be a page that you may want to have out. We'll use this on most of the problems as we're going. Again, growth is when the B value or the rate is positive. Decay is when the B value or the rate is negative. Y is what we're trying to find out. A is our initial value, what we started at. E is that button on the calculator. B is the rate. And then X is whatever we're putting in, some kind of a time, years, months, days, something like that. So for example, we see this all the time with bacterial growth, or also the amount of medicine left in someone's bloodstream as we're doing. But certain bacteria, given favorable conditions, grow continuously at a rate of 12.7% per day. The initial population is 250. Create an equation to model the growth. So again, using our equation, Y is what we're going to be trying to find out. A is our initial amount, that's the 250. Then we are going to use the E button on the calculator when we're trying to calculate it. The percent, remember we move the decimal twice. And in this case it's growth. So it is 0.127. And then X is however many days we're doing. So the equation would be like this with the X. And then the next question down here says, what would it be after 7 days? So then we would type this in, but our x value, the x value is going to be 7 in this case. All right, so to get this into your calculator, hopefully you have one of these calculators. Right here is what we're looking for the E value. Go ahead and take a second and type this whole thing in. Again, it started at 250. Then we used the E. It was 12.7%, so we moved the decimal over. Then we multiplied it times 7 because that's the number of days. And that should be the answer that you got. If you didn't get that, raise your hand, let the teacher pause the video, and help you get that typed in. That's what we're going to be using for most of these problems as we're going. All right, a certain population of bees is decreasing by a continual rate of 4.5%. So again, this is decrease. So when we put this into the B value, it's going to be a negative 0.045. Write the equation to model the population size. So they have the y equal for us. The initial amount is given to us in the table. That's the 50. Then we're going to use the E button, and it automatically kicks you up into the exponent. In this case, it's 4.5% decrease. So we would move this over twice. So 0.045. And then we'll use whatever number of years that we're trying to calculate. So in this case, it would be times 10. Go ahead and put that in your calculators, and let's see what you get. Oh, we did forget. Remember, this is decay. So when you put that in, that needs to be negative. If you put that in your calculator, you should get 31.88. And then if you do the same, oh, the nice thing on the calculators, you don't have to retype that whole thing in again. If you use your up arrow button, arrow back up to that same, you can hit enter. It'll paste it back in, and then you can just go through and change the 10 to a 50. So instead of retyping it, use the calculator so you don't have to keep doing that. And when you put in 50, you should get 5.27. So now doing the graph, we started at 0.50. Then 10 and 32. And we got 20 and 20. 50 and 5.7. Again, we're just estimating a little bit here as we're trying to put it on the graph. And then 100, which is at the end of the graph, and 0.5 right in there somewhere. Then we would connect those dots to get our graph. And that would be the graph of the bees. Again, this is in thousands. So 0.55 that we get down here at the bottom would actually represent 555 bees. So that is an example of the decay, which is what this graph right here is. This one is just zoomed in over the first 10 years. Seems a little more straight, but that's because it's only talking about that little piece right there. So. All right, next one. Again, we use this quite a bit with the amount of medicine in a patient's bloodstream. So in this one, it decays continuously at a rate of 20% per hour. Gives us the initial amount of 5. So 5 is our A value. Then we have the E. In this case, it's decaying by 20%, so that's a negative 0.2. We don't need to 0.20, we can just use 0.2. And then X is going to be the amount of time that it's in the bloodstream. And since we're talking about hours, X is going to be the number of hours. All right, so this one already has those pieces filled in as we're going through. Again, you should be able to type it in one time and then just arrow up, change the T value. They use T here instead of X, so it doesn't matter. I'm just representing time. As you put those in, you should be able to get those values. So at time 0, when the medicine is administered, we have 5 milligrams. After an hour, it drops to 4.1. After 3 hours, it's at 2.7. After 6 hours, it goes to 1.5. And after 10 hours, it goes to 0.7. So if we connect those dots, we get something like that. So now the question is, when does the patient need more medicine? Well, according to this, at 2 milligrams, the patient needs another dose. Well, when does that 2 milligrams hit? Well, somewhere between 4 and 5. So about 4.5 hours, the patient is going to need more medicine. All right. Next example, the proliferation of rabbits after their introduction to Australia is a famous example of population growth. Famous meaning every math class uses it. In 1859, a southern Australian farmer homesick for England imported 24 English rabbits and set them free on his land. Within 6 years, 72 months, Thomas Austin's 24 rabbits had multiplied to 22 million. So we're going to use this to create the equation. The P sub O is just the original population. So again, that's the 24 rabbits that were started. R is the rate, which we didn't have to calculate here. They give us the rate. It's 229% per year. And then T is measured in years. So our equation for this, again, it starts at 24. Then we have the E, and it's being raised to the rate, which again is 229. So when we do this, we still move the decimal twice. So that's going to be 2.29, and then times the T for the number of years. That ends up being the graph. So as you can see, it started off pretty slow. About year 4, it starts to go, and then between 5 and 6, it goes crazy. And again, this is in millions. So by year 7, it's off the chart. We can't see them anymore. So the question is this realistic? Would this actually continue at that rate? Obviously not. At some point, the rabbits kind of have a maximum. That's where we get into the logistic equations, which are the ones that we have next. It does say by 1930s, the rabbit population in Australia had reached 750 million. I don't know what the population of Australia is, but it's probably more rabbits than people. So the logistic equation is this red one. And as they work these out, there is a carrying capacity, which is just a maximum. As you can see, the red one starts to level off in here, and that's the carrying capacity as it goes. So it starts out exponential, and then it curves out and slows into the logistic. So the table below gives the number of European, North American, and South American countries issuing postage stamps from 1840 to 1880. Plot the data and determine whether it's best modeled by exponential or logistic. So all they're asking us here is to put these dots on the graph. So our first one in 1840, there was one country. In 1845, obviously halfway between 40 and 50, there was 3. In 1850, we had 9. 1855 up to 16. 1860 up to 24. 1865 we're at 30. 1870 gets to 34. 1875 we get 36. And 1880 goes 37. All right, so this one, as you can see, we start off slow and then speeds up and then it levels off. So this is an example of the logistic functions. And when they hit that, they'll work towards a maximum, which again is that carrying capacity. The logistic growth model is a little bit of a complex equation, but as long as you have the right calculator, these aren't too bad. We can put the whole thing in our calculator and it'll kick out our answer. And once we get it in the calculator, we don't have to retype it. We can just change the pieces that we want to change. C is the carrying capacity. That's the maximum that it can get to. A is related to the initial amount. Doesn't exactly match up, but it's related to the initial amount. And then B is related to the growth rate. So for this particular example, kind of will remind us of the COVID days a little. On a college campus, 5,000 students. One student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by this equation. Okay, obviously there's a carrying capacity because it can't have more than 5,000 people with it on campus because that's all that they have. That would be every single person. Y is the number of students infected after T days. College will cancel classes if 40% or more of the students are infected. So first we got to know how many 40% would be. So 40% of 5,000 would be 0.4 times the 5,000, which is, 4 times the 5,000 is 2,000. So when it hits 2,000, they're going to close down the campus. They want to know how many after 6 days. That's where you'll type in just like this. So we'll put the 5,000, the fraction bar, and on the bottom we have 1 plus 4,998, or 99, sorry. Then we hit the E button. It kicks us up to the exponent, and then we do negative 0.8 times, in this case, 6, because they want to know what it is in 6 days. That gives us the 118. So that tells us in 6 days, 118 students are going to be infected. So this pink dotted line across here, that's the line that we're looking at. If it crosses, if it goes below that, or excuse me, if it goes above there, that's when we have too many people infected, and we're going to shut the campus down. So we go through and calculate. So again, the first calculation we would do, we don't need to do the 0. We know that one person brought it. But then after 1 day, we would take the t and we would put in 1. Let me get a pen here. So after 1 day, again, we're going to put 1 in for the t. We plug that in. We're going to get 2 people. Again, you don't have to retype this every time. You get it in right the first time, and then just change the t. Just arrow into the same equation, and you should be able to get those values. And now, if we put the graph to that, times 0, it's at 1. When t equals 1, we're at 2. Again, these are 500, so we're almost at the bottom line as we're going. 3, it jumps to 11, which is still way down at the bottom. 6, we get up to 118, so maybe we can kind of see how it's starting to grow. 9, we hit 1,000. So 9, we're just over the 1,000 mark. 12, we get almost to 4,000. 15, we're almost at 5,000. And then 18, we're at 4,986, so nearly the 5,000 one. So there's our graph. Again, it's just going right along the bottom here. Starts to come up just a little, and then all of a sudden it just takes off until it gets to that carrying capacity and kind of slows down. All right, so obviously if they're trying to fight some kind of disease spread, they're trying to work in that 0 to 8 range before it gets into like the 9, 10, 11, 12 day range where it really starts to take off. All right, you have the rest of today to work on your assignment. Again, make sure you have one of these calculators. If you don't have one, you can borrow from the teacher, but you'll need to leave your cell phone with the teacher in order to use one. But you don't want to try and calculate these on a basic calculator. It will take you too long.